Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 12, 2026, just about 6 days ago. It reveals that despite standard filtering efforts, semantic duplicates of test questions are still rampant in training data, affecting 78% of Codeforce's problems and 50% of ZebraLogic tasks. The paper is titled, Soft Contamination Means Benchmarks Test Shallow Generalization. And as we'll see later, these findings cast some serious doubt on whether our current benchmarks are actually measuring true reasoning capabilities. To see where this fits in, Table 1 compares the current study to previous research on data contamination. While earlier papers like Meagher and Schwartz often focused on exact duplicates or small scales, even those that examined semantic duplicates usually missed two critical components. As the central columns highlight, previous works rarely used ecologically realistic fine-tuning data or tested for in-benchmark generalization. The top row confirms that this paper addresses all these dimensions, applying them to large-scale open data. So Figure 2 validates the team's detection strategy by plotting duplicate rates against cosine similarity. On the left for MBPP, the overlapping lines show that even without exact matches, semantic duplicates rise steadily as similarity increases. On the right for Codeforces, however, the lines diverge. The red line spikes at the far right for exact copies, but the blue line peaks earlier, around 0.8. This reveals a specific zone of soft contamination, problems that are semantically identical, but not exact string matches, which traditional filters easily miss. Alright, moving to Figure 3, we might wonder if harder problems are less likely to be contaminated. Here the chart breaks down the percentage of Codeforce's problems with at least one semantic duplicate, organized by their ELO rating, which measures difficulty. The x-axis spans from simple tasks at 800 to very complex ones at 3500. Surprisingly, the bars remain consistently high across the entire board, mostly between 60 and 90%. This shows that problem difficulty does not shield against contamination, so even the toughest challenges in the benchmark are widely present in the training data. Well, distinct from the difficulty patterns in Figure 3, Figure 1 uncovers a stark trend for ZebraLogic puzzles. This chart plots the percentage of exact duplicates found in the training data against the puzzle's grid size. On the left, simple configurations like 2x2 show almost zero contamination. But scan to the right side. For grids 4x4 and larger, duplicate rates skyrocket, consistently exceeding 80%. This suggests that for complex logic tasks, the model is likely relying on rote memorization rather than actual reasoning. Okay, Figure 5 demonstrates how contamination estimates rely heavily on search depth. The charts plot duplicate detection rates against the number of candidate matches reviewed, ranging from the top 1 to the top 100. On the left, MBPP shows immediate saturation. Finding duplicates is trivial. On the right, however, Codeforces reveals a critical trend. Checking only the single best match yields just 28% contamination. But extending the search to the top 100 candidates uncovers that nearly 78% of problems have duplicates. This proves that standard, shallow filters miss most soft contamination. So, while Figure 5 focused on search depth, Figure 4 breaks down these contamination levels across the specific datasets used at each training stage. On the left, looking at MBPP, the saturation is stark. Essentially every training corpus, from pre-training through RL, contains semantic duplicates for over 90% of the benchmark. On the right, Codeforces shows more variation. The orange bar highlights a significant spike during the supervised fine-tuning, or SFT stage, reaching over 50%. This suggests that even if pre-training data is filtered, later instruction tuning can heavily recontaminate the model with test solutions. Alright, having seen where contamination comes from, Table 5 now reveals its deceptive impact on performance. Here, the authors compare models fine-tuned on clean data versus those exposed to just 5% semantic duplicates. Looking at the Olmo 3 results, the contaminated model doesn't just ace the seen examples, it also jumps to 54% on the unseen portion of the same benchmark. This looks like generalization, but the final column tells the real story. On True Detective, a separate reasoning task, the scores stay flat at 28%. Proving the model learned the specific benchmark style rather than gaining any true reasoning ability. To wrap things up, the core message is that modern benchmarks are likely measuring shallow generalization rather than true intelligence. Because semantic duplicates are so widespread, models effectively memorize the test set style without learning the underlying logic. This suggests we need fundamentally new evaluation methods to gauge real progress. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.